So today I will talk about intrinsic parity. So in the earlier lecture I talked about parity. So parity or orbital parity, as I talked about earlier lectures, that parity, or simply sometimes we call it as orbital parity, is independent of species, species of particles, and depends only on the orbital angular momentum state, angular momentum state of system of particles so when creation or annihilation of particles takes place, we have to assign intrinsic parity. We have to assign intrinsic parity to each particle So for any particle A, say A is a particle, state vector is defined as that's AP. So now when operate with parity operator P, the state vector, it gives us eta AP A minus P. So here this is known as the intrinsic parity of the particle. That means eta AP is called intrinsic parity of particle A, right, of the taken particle. So that means, and here the value of eta AP is equal to plus minus 1. And another important thing, that conservation of parity, this is a very important property, that conservation of parity that plus B gives us to C plus D. So let us define initial state. So it is represented by ket I is equal to ket A ket B and ket of relative motion, right? So here ket A and ket B, it describe the internal states of A and B, states of A and B, whereas ket of relative motion, it describe their relative motion and is described by wave function. It is described by a wave function, and this the wave function is given by that RR and YLM theta and phi. Now we assume that parity is conserved in reaction 1 So let us call this as reaction number 1, which I have considered. So for initial state, I can write down eta IP. It can be written as eta AP and eta BP and minus 1 raised to power L, whereas, and this is the orbital momentum, this factor of the orbital parity, and final state I can take it like this: NFP is equal to NCP NDP and minus 1 raised to power L prime. So here eta AP, eta BP, eta CP and eta DP, they are intrinsic parities. Intrinsic parities of A, B, C and D, and minus 1 raised to power L and minus 1 raised to power L prime, they are their orbital parities. They are orbital parities in initial and final states. Final states. So if parity is conserved for reaction 1, if parity is conserved for the reaction given by 1, then we can say that initial parity must be equal to final parity, means final intrinsic parity. Right, so that means NIA and sorry, not N but eta eta AP, eta BP minus 1 raised to power L is equal to eta Cp, eta dP, and minus 1 raised to power L. Thus parity is conserved as multiplicative quantum number. Multiplicative quantum number. This is suggested by this equation number 2, right? So let us have a let me write down a note relating to it. So it's note here I mentioned that parity is conserved. Here in this case parity is conserved, but parity is not conserved always, and if strong and electromagnetic interaction is there, that means parity is conserved, but it does not hold for weak interaction. This means that parity conservation is not universal. Parity conservation is not universal. That's all for this lecture.